Hello, student. So we have seen how the modulated waveforms are generated. Uh, so let's now see how noise affect to that to those modulated signal. Okay. Uh, so it is a noise impact. Okay, the noise impact on modulated waveform. Okay, waveform. So we will try to see this in MATLAB. Okay. So we have generated the modulated signal. Okay. So I hope this is a frequency modulated signal. No? Frequency shift keying signal. Let's see. Yeah, this is a frequency shift keying. Okay. So we will see on BPSK. Okay. So it is somewhat easy because the frequency are same, only the phase shift happen. Okay, so I think it is better to illustrate this noise effect on BPSK modulated signal. Okay, uh, so okay, so if I draw the simple version of BPSK modulator, it will look like this, no? Okay, so we will have a message signal like this. Okay, so this is a binary sequence. Okay, then we have to do the line coding. Okay, and so for a BPSK, normally we are doing unique bipolar line coding. Okay, bipolar line coding. Okay, for BPSK, normally we are using bipolar line coding when we are going to implement a transmitter, when we are going to implement a modulator. Okay, but here you can see that in our simulation we use unipolar NRZ signal for the simulation purpose. Okay, but when we are going to implement it through when we are going to physically implement it, we have to use bipolar line coding techniques. Okay, so I will tell you how it why we need bipolar line coding. Okay, so then we have the modulated signal, sorry, line coded signal. Okay, and here we have a product modulator. Okay, so this will be our BPSK modulator. Okay, so for a BPSK, you know that we need only one basic function. No? For BPSK, we need only one basic function. Okay, let's say it is 5-1T. Okay, so as I can remember, it is look like this, no? 2 AB plus 25 FCT. Okay, so this is our frequency. Okay, so this is the basic function needed for BPSK modulation. Okay, so this is you can find this using Graham Smith orthogonalization procedure. No? Okay, so these are orthonormal function. These are energy signal. This is energy signal, and also this is orthonormal. Okay, this is orthonormal. If you can remember. Okay, please refresh your memory on this. Okay. So maybe this is not exactly same. Okay, I couldn't remember. Okay, but as I can remember, this is the basic function needed for BPSK modulation. Okay, so then we will have the what is that? We will have the modulated output. Okay, so this will be our modulated output. Okay, this will be our modulated output. Okay, and you know that so here after bipolar line coding, okay, here you will have one maybe that is a voltage level. Okay, 1 or -1. Okay, 1 or -1. Okay, So this will be a voltage level. Okay, so this will be a sorry, we know that we have 1 and 0. Okay, we have 1 and 0, and for 1 in bipolar line coding we will assign positive voltage. Okay, and for 0 we will assign minus voltage. Correct. Okay, in bipolar line coding we are going to assign positive voltage for 1 and negative voltage for 0. That is bipolar. We have two polarization. No? Okay, so if we set this voltage level to 4 TB, okay, so this is the energy of the bit. Okay, if you set this positive voltage to read root EB, okay, so that is the voltage level for 1, and minus root TB will be the voltage level for 0. Okay, so for a line coded signal, you will get this kind of signal. Okay, for 0 you have, for 1 you have plus root TB. Okay, and for 0 you have minus root TB. Okay, minus root TB. Okay, so you will get this kind of bipolar signal. Okay, so you have two polarization. This is for 1, this is for 0. 1, 0, so on. Okay, okay. So now so this is a product modulator. Now you are going to multiply this basic function from this voltage value. Okay, so for one you will get root EB 51T. Okay, so this is the waveform for 1. Okay, so this is the waveform or symbol for 1. Okay, so this is the symbol for 1, and for 0 you will have, so if it is 0 you will have minus root TB. So minus root TB 51T you will have for 0. Okay, so here you will have minus CB 51T. Okay, so this is the waveform for 0. Okay, so you know that here you have 0 phase shift, and here you have 5 phase shift. Okay, so this is the modulated signal. Okay, so already we have generated this. Okay, already we have generated this. Okay, already we have generated this. Okay, so if you see our MATLAB code, okay, so here you have NR reset. Okay, but very simply we can how to say, we can convert this to a bipolar signal. Okay, so if your message signal is equal to 1, you can assign plus 5. Okay, let's say that plus 4 2. Okay, so for if your message signal is 0, you can assign minus 2. Okay, so okay, so so this will be your signal. Okay, and you will have this is for 1. Okay, this is for 1. Okay, so you will have plus root TB means 2. Here you can have 2. Okay, okay, and here you will have minus 2. Okay, minus 2. Okay, so this kind of signal you will get. Okay, you will get this kind of signal. Okay, and if I got this, let's see, we will have, we can see a waveform. Yes, okay, so you can see, oh, again we get oh sorry, the frequency should be same. Okay, the frequency I will put here 2, and here also I will put 2. Okay, the frequency should be same, only the phase shift. Okay, so this is this has a 5 phase shift. Okay, that is why it is it have minus sign. Okay, So we will see. Yeah, so I think it is okay. So you can see that here 1 you have 0 phase, and for 0 you have 5 phase. The signal is starting from here with the 5 phase shift. Okay, and this is 1 and this is 0. Okay, so this is okay. Okay, now you know that. Okay, you know that. So this signal will be transmitted. Okay, so this signal will be transmitted. This plus root TB 51T or minus root TB 51T will be transmitted. Okay, will be transmitted through air. Okay, so this will be transmitted through air. Okay, you can directly feed this signal to antenna, and antenna will transmit this signal. Okay, in free space. Okay, so when you are transmitting this signal in free space, okay, so this some noise will be added to this signal. Okay, so noise will be added to signal. So if your signal is, let's say that it is okay, let's say it is plus or minus root TB. Okay, so your transmitted signal will be plus or minus root TB. Okay, plus or minus root TB 51T. Okay, so this is the signal. This is a RF signal. Okay, RF frequency. Okay, so you are sending this signal through air. Okay, so some noise will be added to this signal. Okay, so some noise will be added to the signal. Okay, so this will be your receiving signal. Okay, received signal. Okay, let's say that it is RX. Okay, so this is the received signal. Okay, received signal. Okay, so this is your transmitting signal, and noise will be added, and this the total is received at the receiver. Okay, okay, so now you know that this N we call AWGN, additive white Gaussian noise. Okay, so this will be a random Gaussian random variable. Okay, you can say like this. Okay, so it is normal. So it will be 0 means and some variance with some variance. Okay, so this is a Gaussian random variable with 0 means and with some variance. Okay, so you know that this variance is referred with the power of the noise. Okay, so this is the power of the noise. Okay, power of the noise. Okay, so what you have to do, you have this signal. Okay, you have this signal, and you can generate some noise variable. So this will be a Gaussian variable. Okay, so this will be a Gaussian variable, the standard Gaussian variable. Sometime we get this as a complex Gaussian variable also. Okay, so this will be a complex or normal Gaussian variable. Okay, in this case we will take it as a normal Gaussian variable. Okay, because no any imaginary part is there with our simulation. Okay, but when we are doing QPSK, we will have imaginary parts. Okay, so sometime when we are dealing with QPSK signal, we get this noise as a complex Gaussian noise. Okay, but here we will get it as a normal Gaussian noise. Okay, so power, so this sigma is the power of the noise. Okay, so what we can simply do, okay, so here we have our signal. Okay, we have our transmitted signal. So transmitted signal is look like this. We have already seen it. Okay, so the transmitted signal is look like this. Okay, so where is the, so if I run this, okay, it will take some time because, okay, so this will be our transmitted signal. Okay, so transmitted signal is like this. Okay, so you know that when we are transmitting, the noise will add to every point. Okay, every point. Okay, so I will generate a noise variable. Okay, I will generate a noise variable. So how to generate a noise variable in MATLAB? Okay, so there are many standard methods. Okay, you can find Google. okay, as usual. Okay, so if I find Google, okay, so generating Gaussian random numbers in MATLAB, okay, not in Python, in MATLAB, okay. So you can see this command you can take to generate the noise, the this statement, this code you can use to generate normal random numbers, okay. So I take this, okay, I take this, okay. So this will be my noise, okay, AWGN, additive white Gaussian noise, okay. So this is mean, okay. So we have zero mean signal, okay, and sigma means the standard deviation, root of sigma square, no? So that is standard deviation, okay. So this is the variance, okay. So this is the variance, okay. So you have to put sigma here. That means that is the standard deviation, no? Okay, square root of this variance, okay. So that that refer the power actually, okay. That refer the power of the noise signal. So I will put 1, okay. So how many noise number should I generate, okay. So very simply you can so I think like this, okay. Very simply you can determine the number of noise value we should generate. How? Okay, so you know that. So now we are going to add this noise to the modulated signal, okay. So now we are going add this noise, okay, to this modulated signal. So this is our modulated signal, okay. So can you remember that we have used T 1 to n, okay, 1 to n to generate this signal, okay, modulated signal, okay. And we have some values here, okay. We have some values here, okay. So if you can generate the same number of values for AWG, okay, and if you add them together, okay, so every calculated point you will add the noise value, no? Every calculated point you will add the noise value. So we will do like this, okay. We will do like that. So here you can see that we are using this 0 to 0.1 n, okay. So I am going to generate so this will be also an array, okay. Array with row 1, okay, row 1, okay, and I get it as length t, okay. This, I hope you can understand this, okay, what I'm doing here, because now I am going to generate, okay, I'm going to generate some random numbers, okay, from some random numbers. So if I run this, okay, if I run this, okay, so here you have get AWGN, okay. So this is the Gaussian noise, okay. So you have generated, okay, you have generated some Gaussian numbers, Gaussian random variables, okay, Gaussian random numbers with zero means and standard deviation 1, sigma 1. So this one refer to the power, okay. So that is very important. This one refer to the power, okay. So so here we have generated 1 to length 3 numbers, okay. So we will have 401 values. Okay, so if you look at this, the modulated signal MW, that also array, no, that also array. Okay, that also array, and it also has 401 value. Okay, 401 value. That is why I generated 400 value here. Okay, so if I add these together, if I add this modulated array, so this will be our so here these value are related with our signal, no, these values are related with our signal. So if I add MW, so it will be our transmitted waveform. Okay, so this will be our transmitted signal MW, modulated waveform. Okay, plus, and we have to add AWGN, the noise. Okay, here. Okay, I have write this one. Okay, I have write this one. So this will be MW. Okay, so we have, you know, that Rx, the received signal should be plus or minus root TB. Okay, U1T plus N. N means AWGN, average white Gaussian noise. Okay, so in our simulation, we put this information into MW array. Okay, so we have 401 element. Okay, and we have generated AWGN value. Okay, which also has 401 element. Okay, then we will add them together. Okay, so we will get this kind of signal. Okay, with our transmitted signal information and noise information, noise value. Okay, so that will be our received signal. Okay, so I will put here, so this will be our received signal, Rx, let's say Rx. Okay, so now I think we have added the value. Okay, so we can plot it here also. Okay, okay, I will plot this in separate page, separate column. Okay, so we can do it like this. Okay, subplot, we are going to we are going to divide our the area into 3 column, 3 rows and 1 columns. So this will be our first position. Okay, and so here this will be our second position. So here we have to put 2. Okay, and this will be the in first row we have the unipolar line coded signal in the first row. In the second row we have modulated signal or transmitted signal. Okay, so this will be our transmitted signal. Okay, and in next column, okay, next column, I will plot our received signal. So it is also with respect to T. Okay, so here we have T also 401 values. Okay, so we can plot it with respect to T, Rx. Okay, so this will be our signal. Okay, so I will use green color to show that. Okay, so I will use green. So if I run this, okay, if I run this, so let's see what will happen. Yeah, this should be 3. Okay, this should be 3. Okay. So we will run it again. Okay, I think now you can understand what is this subplot code. What is the use of this subplot code? Okay, so here you can see that subplot. Okay, we are plotting different plots. Okay, different plot in the same page. Okay, so we are going to break this page into 3 columns. Okay, and 1 row, sorry, 3 rows. Okay, and 1 column. Likewise, you can you can break this page into required columns and required rows and required column. Okay, like this. So if you put 2, you will be having 4 rows and 2 columns. So altogether you will have 8 break page. Okay, 8 section. Okay, so you can draw 8 subplots in the same page. Okay, so you can see that so this will be our the line coded signal, and this will be our modulated the transmitted signal, and this will be our received signal. So you can see that some noise has added to the signal. Okay, uh, so still you can see that we can get the signal from here because it is slightly so still we have the shape of the signal. No phase informations are there. So here you can see that 0 phase, and here you can see that 5 phase. Okay, so I think using this signal we can get the signal back. Okay, so if you put this power as 0, okay, so this will be the power of the signal. So if you put 0 power, that means there is no value. No? So let's see what happens. Okay, so you can see that the same signal we have, because here the power of the noise is 0. That means no noise power. Okay, there is no noise power. So if you put very small noise power, let's 0.1. Okay, let's say it is 0.5. If otherwise you can't observe it. Okay, okay, you can see that now we have very less noise now, because the noise power is very small. Okay, so this variance, okay, so this is the sigma, so it referred to the variance. Okay, so it referred to the power. Okay, this point, this is mean, and this will be the sigma, the square root of variance. Please keep remember that variance is always related with the power. Okay, so if I put 1.2 power, that means very less power. Okay. So you can see that now the signal is affected very slightly. No, we have almost we we have the almost transmitted signal here also. This is the transmitted signal, and this is the received signal, and here we almost have the transmitted signal. No? Okay. Okay. So if I add a very huge power, let's say that 5 or 6, 7, 8, okay. So what happened? Okay, now you can see that the signal is very distorted. No, signal is much distorted. Actually, sometimes we couldn't recover this transmitted signal from this received signal. No, this transmitted signal couldn't recover from this received signal. What we are doing here actually, okay, what we are doing here, we didn't change the power of the transmitted signal. We didn't change the power of the transmitted signal. Okay, but we change the power of the noise. Okay, okay. So we here, so this will be our transmitted signal. Okay. So this will be our transmitted signal. Let's say that it is so that is the signal. So that signal have some power. Let's say that it is a signal power, and here you have noise power also. Okay, you have noise power. Let's say that is N. Okay, so this will be your SNR, no, signal to noise ratio. Okay, if you put 10 log 10, this will be SNR dB value. Okay, so you can see that here we we didn't change the signal power. It is constant, and we change the noise. That means we are changing the SNR, no? We are changing the SNR, okay? So you can see that for different SNR. So you can see that if you have very low power, that means SNR is very high, okay? So that you will get a good signal, no? Good received signal. Okay, you have seen it, okay? So now, if this N power is very high, it is 8, 9, 10 or some level, okay, so that means SNR is very low. Okay, at that time you will have very distorted signal, no, very distorted signal. Okay, so that is that. Okay, so this is the idea you should take. Okay, and this is the way how to add some noise information to a modulated signal. So I think you get the idea. Okay, okay, let us stop.